One use of the chain rule is to be able to do a problem from Calculus 1 in a much easier fashion. And you might remember in Calculus 1 the idea of implicit differentiation, when there might have been a relationship xy that couldn't be solved explicitly for y. And what we had to do is we had to use a technique called implicit differentiation to be able to find the slope at a specific point. And generally it's a pretty rigorous process algebraically. There's a much easier way to do this by using something called the implicit differentiation theorem. And the implicit differentiation theorem says that if we have not a function, but if we have a multivariable function xy, and we want to be able to find the derivative y with respect to x, we could basically change that into a chain rule type of problem, and we could take and set that equal to a function f, and then we could say df dx, and then divide by df dy, and then take the opposite of that, and that's going to give us dy dx. All right. So all we're really doing is we're just taking dy dx, and we're just taking the reciprocal of it and dividing it out, and then just making partial f, and dividing each of that by dy dx, and then doing the reciprocal of that to get that opposite in there. All right. So pretty easy verification of it. So that's the formula we're going to use. And f is just going to be the multivariable function set equal to 0. So I'm going to show you an example where we go and do it the old way, and then I'm going to show you how easy it is to use the implicit differentiation theorem, where you can just take fx, fy, divide them, and take the opposite. So let's take a look at this function. Or not function, but relationship, x squared minus xy plus y cubed equals 8. The old way of doing this, okay, so this is the old way. And for those of you that don't care, you can go ahead and just skip this part if you want to. But for those of you that care to see the old way of doing implicit differentiation, just in case you've forgotten, you're going to just go through and you're going to take the derivative of everything with respect to x normal. Anytime you take a derivative with respect to y, you multiply by a factor of dy dx. All right, so the old way of doing this, the derivative of x squared, 2x. The derivative of negative xy is a product rule, because we have a function of x and a function of y. So we're going to have derivative of x is 1 times y. Derivative of derivative of y is going to be 1, but then we multiply by dy dx. The derivative of y cubed, 3y squared, dy dx. Derivative of 8 is 0. And you might remember that at this point, what you want to do is you want to solve for dy dx. All right? So I'm going to distribute the negative. I'm going to put everything to one side that doesn't have a dy dx. So by just doing a little bit of algebra, we get opposite x dy dx plus 3y squared dy dx is going to be equal to y minus 2x. And then finally, we could probably see that we can factor out dy dx. And that'll leave us with negative x plus 3y squared is equal to y minus 2x. And then we can divide both sides by this negative x plus 3y. So ultimately, dy dx is going to be equal to y minus 2x divided by negative x plus 3y. If we changed all the signs around, in other words, we just multiply the top and the bottom by negative 1, or if we factor out a negative 1, another way to write this is 2x minus y divided by x minus 3y. All right, so, and I just did that just in case we get one of these two solutions. All right, we're probably going to get one of those two for the implicit differentiation theorem, but I just want to make sure we have them both so that way when we get the answer, we can just refer back. All right, that's the old way. Now, let's now use the formula dy dx is equal to the opposite of fx over fy. And so fx, now we do have to set this equal to 0, so that's going to be x squared minus xy plus y cubed minus 8 equals 0. Not that it matters much. Okay. Fx is going to be 2x squared minus y. All right, so I'll just write that down here. So 2x squared minus y. Or, I'm sorry, 2x minus y. We don't need a square in there. So we have 2x minus y. And then we're going to divide that by the derivative of y. And I did forget a square, excuse me. All the way down here. Notice that there was a square here. That was in the old way of doing that, so sorry about that. And so up here, if we take the derivative with respect to y, that's going to be negative x plus 3y squared. And if we just multiply the denominator by this negative 1, then we would get 2x minus y over x minus 3y squared. And that's exactly the same solution. All right, so obviously the implicit differentiation theorem is much easier to work with. Okay, so now that's not a proof that it works, it's just a justification. All right, a proof would be going through and showing that it works for any case whatsoever. All right, let's see a second example. So we have this cos x minus y equals x e to the y. Right? So let's start by defining our function f to be cos x minus y minus x e to the y. Right? Just by setting those equal to 0. Right? And then from there, what we can do is we could just go ahead and we can find fx. So remember, dy dx is going to be equal to the opposite of f sub x over f sub y. F sub x is going to entail a chain rule for at least the first term. So f sub x, and I should squeeze that negative in there somewhere. So let me just erase this. Give ourselves a little bit of room. So we have derivative of cos is negative sine of x minus y, and the derivative of x interior is 1. Right? I'll clean this up after we're done. And then in the denominator, oh, and of course we still have that negative x e to the y. That's going to be negative e to the y. And then if we take the derivative with respect to y, then we're going to get, again, a negative sine x minus y. We're going to multiply by the interior derivative with respect to y, which is a negative 1. And then finally, derivative of negative x e to the y with respect to y is negative x e to the y. All right. Now, if we simplify this, we have a negative and a negative for one term on top and a negative. So those all become positives. And then we have a negative and a negative here, which becomes a positive. So fortunately, we only have to deal with one negative after cleaning this up. So a more clean answer for this would be sine x minus y plus e to the y divided by sine x minus y minus x e to the y. All right. And unfortunately, although they're really, really close to one another, the numerator and the denominator, unfortunately, we can't do anything to really simplify this. So we're kind of stuck with that answer. However, it is pretty cool that now we can see how easy it is to find the derivative instead of using implicit differentiation and the slope at a specific point of a multivariable function.